February 3, 1942. Quonset Point Naval Air Station, Rhode Island. A Navy engineer stood in the freezing wind, watching steam rise from his coffee as he studied blueprints weighted down with wrenches. Otto Brandenberger had 60 days to solve a problem that threatened every American base from Hawaii to Australia. Reports arriving daily described tents collapsing under tropical storms, wooden barracks rotting in humidity, supplies ruined by rain before enemy action could touch them. On Guadalcanal, commanders were losing more equipment to weather than to Japanese bombing. The math was brutal and undeniable. Traditional construction methods required months, skilled carpenters, and lumber that simply didn't exist in sufficient quantities. What the Navy needed was a building that acted like equipment. Something that could be crated, shipped, and assembled by 6 men with hand tools in a single day. Something that could survive a typhoon and cost less than a truck. Brandenberger's team had drawn inspiration from British Nissan huts, but those designs failed in the tropics. The solution would need to be different, better, and ready for mass production before summer. December 8, 1941, Washington, D.C. A Bureau of Yards and Docks situation report landed on the Chief of Naval Operations desk. The pages documented infrastructure losses from Hawaii to Guam with clinical precision. Rear Admiral Ben Morale read the numbers twice, hoping he'd misunderstood. He hadn't. The report showed that U.S. forward bases lacked adequate shelter for the 300,000 men projected to deploy by mid-1943. Existing doctrine treated shelter as secondary to tactical installations. Build the runway, then the fuel depot, then worry about where personnel sleep. That logic worked in peacetime California. It was failing catastrophically in the Pacific. Wake Island reported 90% of wooden structures destroyed by December storms before Japanese forces even arrived. Equipment sat exposed to salt spray. Rations spoiled without covered storage. Medical supplies degraded in tropical humidity. On Guam, 80% of temporary barracks had failed within 3 weeks of construction. The human cost was measurable and growing. Hospital commanders reported a 40% increase in malaria and dysentery cases among South Pacific troops. The correlation was direct. Men sleeping in wet tents and operating without weatherproof facilities were getting sick faster than combat could wound them. Lieutenant General Brehan Somervell, commanding Army Service Forces, received similar reports. His logistics staff compiled data showing that several island commands logged greater equipment losses to weather than to enemy action in the war's first 6 months. This metric forced immediate recognition. Weather wasn't a secondary concern. It was an active threat requiring an engineering solution. The War Department's mid-1942 deployment forecast projected more than 1.5 million personnel overseas. Navy circulars elevated temporary prefabricated buildings to top 5 logistical priorities, ranking alongside ammunition, fuel, and food. The emphasis reflected new understanding. Without adequate shelter, everything else failed. Troops got sick, equipment corroded, operations degraded. The construction challenge was unprecedented. Traditional wooden barracks required skilled carpenters, weeks of labor, and lumber that was increasingly scarce as war production consumed forestry output. A single standard barracks took 12 weeks from foundation to completion. Scaling that timeline to house 1.5 million men was mathematically impossible. Weather losses and disease rates drove a fundamental requirement. The military needed industrialized shelter, buildings that could be manufactured like weapons, shipped like ammunition, and erected like tents. The solution would need to combine the permanence of wooden structures with the portability of canvas, at a cost the military could sustain across thousands of installations. In the war's first 6 months, commanders learned that even winning tactical engagements meant nothing if disease and exposure destroyed combat effectiveness. The lesson was expensive. The response would need to be revolutionary. January 5, 1942. Davisville, Quonset Point, Rhode Island. Otto Brandenberger unrolled British Nissan Hut drawings beside U.S. Navy specifications. The 1916 design had proven robust in European conditions. But reports from British forces in Burma and Malaya told a different story. The all-metal semicircular huts became unbearable ovens in tropical heat. Interior condensation created perpetual dampness. Galvanized coatings corroded rapidly in salt environments. The Nissan worked in France. It failed in the tropics. The American version would need to solve problems the British design had never encountered. Brandenberger led a small team. Albert E. Mead, superintendent from the Fuller Company, brought construction expertise. Liaison engineers from Strand Steel Corporation provided steel fabrication knowledge. Together, they had weeks to design something that would transform military logistics. The fundamental challenge was aerodynamic. Pacific typhoons generated wind speeds exceeding 150 miles per hour. Traditional gabled buildings became sails, lifting off foundations or collapsing under lateral loads. The solution required understanding how wind interacted with curved surfaces. MIT wind exposure studies under Project 42B had tested various building shapes. The data was clear. Semicircular profiles reduced lateral wind pressure by 37% compared to gable roofs. The curved surface deflected wind, rather than resisting it, converting destructive force into aerodynamic flow around the structure. The team established core specifications. Standard modules would measure 16 feet wide by 36 feet long, providing 960 square feet of floor space. The structure would use continuous corrugated galvanized steel sheathing over lightweight steel ribs. The ribs would form unbroken arches, providing inherent strength without bolted joints that could fail under stress. Wood end walls would accommodate doors and windows while allowing field modification. Plywood flooring would rest on treated joists. The entire design prioritized simplicity. Fewer unique parts meant faster manufacturing. Standardized components meant easier assembly. Lightweight materials meant reduced shipping weight. The critical innovation was eliminating concrete foundations. Island conditions often meant construction on coral, sand, or volcanic rock, where traditional foundation work was impossible. The Quonset would anchor using steel stakes driven into ground or held by sandbags on coral. The semicircular shape distributed loads evenly, allowing the structure to sit directly on prepared surfaces. Davisville exposure stand logs documented prototype testing. Engineers subjected scale models to simulated wind loads, measured stress points, and identified failure modes. The testing revealed that the continuous arch design transferred loads smoothly through the structure without creating stress concentrations. The shift from bolted rib segments to continuous arches was crucial. Previous semicircular shelters used segmented ribs bolted together. Each connection point represented potential failure under extreme loads. Continuous ribs eliminated those vulnerabilities entirely. The structure became a single unified element rather than assembled components. Assembly time drove every design choice. 6 men, with hand tools, needed to erect a complete shelter in 8 hours. That requirement forced radical simplification. Components needed to be light enough for manual handling. Connections needed to be simple enough for untrained personnel. The entire assembly sequence needed to be foolproof. The design used minimal fasteners. Steel panels connected with self-tapping screws. Ribs slid into place without complex alignment procedures. Wood end walls attached using standardized bolt patterns. The flooring system allowed adjustment for uneven ground. Every element was designed assuming assembly crews had no construction experience and minimal supervision. The result was revolutionary. A prefabricated building that required no skilled labor, no concrete work, no heavy equipment. A shelter that could be packed into 12 standardized crates, weighing 7,000 pounds total. A structure that 6 men could assemble in a single workday. The procurement branch reviewed preliminary designs in late January. The specifications seemed impossible. Traditional barracks cost $3,000 and took 12 weeks to build. This design promised similar capacity for under $1,000 and 8-hour assembly. The claims seemed too good to be true. But the timeline left no room for skepticism. Theater loss data showed weather destroying more material than combat. The procurement branch greenlighted pilot production lots before full tropical trials. The acceleration violated normal procurement procedures. The situation justified the risk. February through March 1942, Quonset Point and Dahlgren Proving Ground, Virginia. A test officer at Dahlgren recorded overpressure readings during blast simulation trials. The semicircular Quonset prototype sat 50 feet from a controlled detonation designed to produce 5 pounds per square inch overpressure at that distance. The test simulated near-miss artillery or bomb strikes. Expectations were modest. The structure was temporary shelter, not permanent fortification. It should provide reasonable protection against fragments and weather. Complete survival of blast effects seemed unlikely given the lightweight construction. The detonation produced the calculated overpressure. The Quonset flexed visibly as the shockwave hit. Steel panels deformed slightly. The structure moved on its anchors. Then it settled back into place. Inspectors examined the results. Several panels showed buckled corrugations. The end wall had cracked, but the fundamental structure remained intact. The continuous arch design had distributed the blast load without catastrophic failure. More importantly, the damage was repairable. Replacement panels could be bolted in place within hours using standard components. The test results exceeded all predictions. The Quonset wasn't just weatherproof temporary shelter. It was blast-tolerant structure, capable of surviving combat conditions and returning to service after field repairs. Navy test boards supervised additional trials. CB cadre, scheduled for assembly training, erected test units under observation. The assembly sequence was timed repeatedly. 6 men with hand tools consistently completed erection in under 8 hours. Untrained personnel achieved similar results with minimal instruction. The kit packaging was refined through these trials. 12 crates contained all components. Total shipping weight remained under 7,000 pounds. The crates measured standardized dimensions compatible with Navy cargo handling equipment. Everything about the design reflected logistics optimization. Component lists documented fewer than 15 major parts: steel arch ribs, corrugated panels, wood end wall sections, plywood flooring, hardware kits. The simplicity enabled both rapid manufacturing and foolproof field assembly. Staking and anchoring schemes accommodated different foundation conditions. On soil, steel stakes driven 36 inches provided secure anchorage. On coral, sandbags placed around the perimeter and over floor edges prevented movement. The flexible anchoring system meant the same basic design worked on any surface. Budok's contract authorization arrived in early 1942 for initial mass production runs. The model designation and component specifications were finalized. The Quonset Hut transitioned from experimental prototype to standardized deployable system. The approval velocity was unprecedented. From design start to mass production order, approximately 60 days elapsed. No other U.S. wartime building type achieved that speed. The compression reflected both the urgency of the requirement and the effectiveness of the design solution. Traditional military construction moved slowly. Arsenal engineers spent months perfecting specifications. Procurement review boards debated contractor selection. Pilot production ran for quarters before full-scale authorization. The Quonset program eliminated most of that process through necessity. There simply wasn't time for conventional procurement timelines. The result demonstrated that engineering excellence combined with urgent necessity could accelerate innovation dramatically. The same design process that typically required years had produced a deployable system in weeks. The compressed timeline didn't compromise quality. It forced ruthless focus on essential features and elimination of unnecessary complexity. April through December 1942. Detroit, Cleveland, Chicago. A press line at Great Lakes Steel stamped corrugated steel arcs where automobile frames had moved months earlier. The machines operated continuously. 3 shifts. 7 days weekly. The output exceeded all projections. Pre-war barracks required skilled carpenters and weeks of labor. Quonset kits shipped from factories within days of order placement. The transition from craft construction to industrial production transformed military building supply. Plant managers at Strand Steel and other contractors coordinated with Navy inspectors. The specifications were precise. Panel dimensions, corrugation depth, galvanization thickness, hole placement. Everything was standardized to ensure interchangeability. Parts manufactured in Detroit needed to fit perfectly with components from Cleveland. Tooling development for standardized panels required significant upfront investment. Dies for stamping corrugated sheets cost thousands of dollars each. Jigs for assembling ribs demanded precision machining. Quality control equipment needed calibration against Navy standards. But once tooling was complete, production scaled rapidly. The same automotive mass production methods that built cars by the thousands applied equally to building components. Stamping operations, welding sequences, coating processes, all were optimized for volume output. Galvanization schedules ensured corrosion protection. Steel panels received hot-dip galvanizing, producing zinc coatings that would resist corrosion for years, even in tropical conditions. The coating thickness exceeded commercial standards, reflecting military requirement for durability under extreme conditions. Jig assembly for ribs maintained dimensional accuracy. Each rib needed to be identical. Variations would prevent panels from fitting properly during field assembly. The jigs ensured that ribs produced in different factories at different times remained perfectly interchangeable. Quality control reject rates remained below 2%. Inspector teams checked dimensions, welds, coating thickness, and hole alignment. Defective parts were scrapped or reworked. Only components meeting specifications shipped to assembly points. The reject rate demonstrated that mass production could achieve precision when properly implemented. Unit cost stabilized around $800 in 1942. That figure included all materials, manufacturing, crating, and shipping to port. The cost was roughly 1/4 that of equivalent wooden barracks and required a fraction of the construction time. Navy contractor lists grew to approximately 10 primary manufacturers. Each operated multiple production lines. Weekly output reports reached several thousand units by mid-1943. The distributed production provided resilience against disruption while enabling massive scale. By year's end, Quonset huts were cataloged as standard deployables, shipped alongside hospitals, power units, and aviation spares. The structures had transitioned from emergency expedient to standard infrastructure component. Logistics planners included Quonsets in deployment packages automatically, like tents or vehicle parts. The transformation from experimental prototype to mass-produced equipment happened in months. That acceleration reflected several factors. The design simplicity enabled rapid manufacturing scale-up. The modular approach allowed distributed production across multiple contractors. The standardization meant suppliers could tool up independently while maintaining interchangeability. Most critically, the urgent requirement justified extraordinary resource allocation. American automotive industry had developed mass production methods that could manufacture complex assemblies at extraordinary scale. Applying those methods to building components was logical extension. The Quonset demonstrated that anything that could be broken into standardized parts could be mass-produced, regardless of size or complexity. November through December 1942. Guadalcanal, Solomon Islands. Seabees from the 6th Naval Construction Battalion opened stenciled crates in driving monsoon rain. Water ran in sheets off their ponchos. The ground was already saturated. Wooden supply crates were disintegrating. Canvas tents had collapsed hours earlier under the deluge. The battalion engineering officer had ordered Quonset assembly despite the conditions. The men needed dry shelter. Medical supplies needed weatherproof storage. The operations were scheduled regardless of weather. 12 Quonsets were erected over 36 hours while rain continued. The assembly crews worked in shifts. They discovered quickly that the semicircular design shed water naturally. Rain didn't accumulate on the curved surface. It ran off immediately, keeping interior spaces dry even during construction. The monsoon continued for 48 hours, dropping 16 inches of rainfall. Traditional wooden structures showed stress damage. Canvas tents were complete losses. But the newly erected Quonsets remained operational without structural failures. Battalion after-action reports cited 0 structural problems during the weather event. The documentation was significant. Combat reports were notoriously skeptical of new equipment. Field units routinely criticized designs that failed under operational conditions. The 6th NCB's endorsement carried weight because it came from experienced construction personnel under combat conditions. Marine logistics officers noted improved supply management. Dry storage prevented food losses that had plagued earlier operations. Medical kits remained serviceable instead of degrading in humidity. The operational impact extended beyond simple shelter. Reliable weatherproof structures enabled sustained operations that had been impossible with canvas and deteriorating wooden buildings. The field assembly sequence proved practical under real conditions. Anchoring on coral used sandbag methods exactly as designed. Integration of blackout measures required only draping canvas over window openings. Fragment shields could be improvised using sandbags stacked against walls. Quartermaster officers calculated the efficiency gains. Dry storage correlated with fewer food losses. The reduction exceeded the capacity of an additional supply ship. Weather protection delivered logistics improvement equivalent to increasing delivery tonnage. That arithmetic made Quonsets more valuable than their cost suggested. The Guadalcanal experience provided crucial validation. Laboratory tests had proven the design worked in theory. Field deployment under combat conditions proved it worked in practice. The difference mattered enormously to procurement decisions and operational planning. March through September 1943, Bougainville and New Caledonia. Interior thermometer readings inside a standard Quonset exceeded 110 degrees Fahrenheit at midday. The all-metal construction absorbed solar radiation. Heat transferred to interior air rapidly. Personnel inside were operating in conditions that approached heat exhaustion limits. The initial design assumption was universality. One model would serve all conditions. The tropical deployment experience proved that assumption wrong. Heat and humidity created problems that temperate testing hadn't revealed. Army Quartermaster Corps test teams documented the issues. Interior temperatures during tropical midday made the structures nearly unusable. Condensation formed on interior surfaces during night cooling, creating moisture problems. Corrosion appeared on fasteners and panel edges, despite galvanization. Navy civil engineers analyzed the feedback. The fundamental design was sound. The modifications needed were specific adaptations for extreme conditions, not comprehensive redesign. The jungle-type Model 14 emerged from this analysis. Ridge vents along the apex allowed heat to escape through convection. Screened louvers in end walls provided cross-ventilation. Reflective coatings on exterior surfaces reduced solar heat absorption. Metallurgical changes addressed corrosion. Higher zinc galvanization provided better protection. Asphalt underseals on panel edges prevented moisture intrusion. Field-applied aluminum paint added an additional reflective layer. Temperature studies documented the improvements. Ridge vents and reflective coatings reduced interior temperatures by 10 to 15 degrees Fahrenheit, compared to standard models. The reduction wasn't dramatic, but it moved conditions from dangerous to tolerable. Maintenance logs showed coating treatments doubled panel lifespan in tropical service. Untreated panels began showing corrosion damage within 6 months. Treated panels remained serviceable for over a year before requiring maintenance. The iterative improvement process demonstrated effective engineering feedback. Field units identified problems. Engineers developed solutions. Modifications were tested and incorporated into production. The cycle operated rapidly because the basic design allowed bolt-on improvements without fundamental redesign. Medical reports correlated environmental improvements with health outcomes. Reduced interior temperatures corresponded with decreased heat exhaustion incidents. The connection transformed a building modification into a measurable health intervention. The Quonset wasn't just shelter. It was equipment that improved personnel combat effectiveness. The climate-specific variants demonstrated design flexibility. The semicircular arch could accommodate different internal configurations, ventilation systems, and surface treatments. Standardization didn't mean inflexibility. It meant a common platform that could be adapted to specific requirements. Late 1943 through early 1944. Tarawa Atoll and Bougainville. Wind damage survey teams mapped debris fields after a major tropical storm struck Tarawa. The documentation was systematic. Location, building type, damage severity, reconstruction time. The data would inform future construction standards. Gabled wooden barracks showed widespread failures. Roofs separated from walls. Structures collapsed completely. The damage patterns indicated wind loads exceeded design limits by significant margins. Quonset arch structures showed localized panel loss but intact frames. The semicircular shape had performed as aerodynamic testing predicted. Wind flowed over the curve without generating uplift sufficient to destroy the structure. Panels that failed could be replaced. Frames that survived could support repairs. Naval Construction Battalion survey officers documented performance through wind events estimated at Category 4 equivalent intensity. Sustained winds exceeded 130 miles per hour. Gusts reached higher. Those conditions destroyed most conventional structures. The curvature's aerodynamic advantage was measurable. Uplift force on curved surfaces was dramatically lower than on flat surfaces. The continuous arch distributed loads smoothly without stress concentrations. The anchoring system held because loads remained within design limits. Recommended improvements emerged from storm damage analysis. Partial berming, earth piled against lower portions of walls, reduced wind loads on the structure's base. Sandbag skirts around perimeters prevented wind from getting under the structure. The modifications were simple, using materials available in field conditions. Standardized repair panels simplified reconstruction. Damaged sections could be replaced using components identical to original construction. Time to repair metrics were measured in hours, not days. The rapid repair capability meant installations could return to operation quickly after storm damage. Field reports emphasized survivability. Quonsets weren't indestructible, but they were repairable. That distinction mattered operationally. Losing a building temporarily was acceptable. Losing it permanently required complete reconstruction. The Quonset's repairability meant storm damage was temporary setback rather than permanent loss. Depot logs showed an unplanned benefit. Fewer replacement kits were needed after storm seasons than procurement planners had anticipated. The structures survived better than expected. The shipping economy was significant. Cargo space allocated for replacement shelters could carry ammunition and fuel instead. Island command engineers noted the pattern. Storm-resistant structures reduced logistics burden. That reduction freed transport capacity for other requirements. The indirect benefit exceeded the direct cost savings. The Quonset delivered value beyond its primary function. 1944. Tinian and Saipan, Mariana Islands. Aerial reconnaissance photographs showed expanding arrays of semicircular rooflines beside runways. The pattern was distinctive and unmistakable. From altitude, Quonset installations looked like rows of silvered arcs catching sunlight. The initial expectation was troop housing. The operational reality expanded far beyond that limited role. The 4,000-square-foot Warehouse 40 models housed depot operations, motor pools, and surgical wards. The adaptability transformed the Quonset from shelter into industrial infrastructure. The 40-foot by 100-foot span required structural modifications. Truss reinforcement at bases strengthened the larger arch. The design retained the semicircular profile while scaling to warehouse dimensions. Modular partitioning divided interiors for different functions. Lighting and ventilation kits adapted commercial systems to military requirements. Medical variants included specialized features: sterilization rooms with sealed partitions, ventilation systems with filtered air supply, electrical systems supporting surgical lighting and equipment. The Medical Corps configured Quonset surgical wards that provided capabilities previously requiring permanent hospitals. CB regiment staff documented construction pace. In 312 huts erected in 30 days on Tinian represented extraordinary throughput. The assembly rate exceeded 1 hut every 2 hours, sustained for a month. That pace was possible only with standardized components and proven assembly procedures. Unit diaries noted approximately 28% logistics efficiency gains with consolidated storage. Supplies previously stored in scattered open areas could be organized in weatherproof warehouses. Inventory control improved dramatically. Damage rates declined. The operational improvements justified the infrastructure investment. The evolution from shelter to industrial enclosure enabled sustained air operations. B-29 Superfortress operations from Tinian required massive logistics support. Bombs, fuel, spare parts, maintenance facilities. The infrastructure supporting those operations increasingly relied on Quonset structures, providing controlled environments for critical functions. On Tinian, covered floor area increased faster than runway length. That reversal of typical base growth patterns reflected operational reality. Aircraft could operate from minimally developed fields if logistics infrastructure supported them. The infrastructure increasingly meant Quonset provided facilities. The scale became visible in supply statistics. Tinian's Quonset facilities contained more covered storage space than most pre-war military installations. The coverage was assembled in weeks rather than years. The speed enabled operational capabilities that traditional construction timelines couldn't support. Sortie generation rates correlated with logistics infrastructure quality. Bases with adequate covered storage, maintenance facilities, and supply organization generated more sorties per aircraft than bases lacking that infrastructure. The Quonset contribution to air operations was indirect but measurable. Better infrastructure meant better operational capability. 1944. Port Hueneme, California, and Adak, Aleutian Islands. A calibrated anemometer at Port Hueneme registered test gusts above 100 miles per hour. Engineers documented frame deflection, panel stress, and anchoring loads. The wind tunnel testing had predicted performance. Field trials validated the predictions. In Adak, wind chill readings dropped below -40 degrees Fahrenheit. The Arctic conditions tested completely different limits. Materials that failed in tropical heat might fail in extreme cold. Seals that worked in temperate zones might crack in freeze-thaw cycles. The testing revealed how a single design performed across Earth's environmental extremes. Naval Construction Battalion Center test directors supervised Arctic trials. Mineral wool insulation filled the spaces between ribs and interior panels. Vapor barriers prevented condensation on cold surfaces. Oil stoves provided heating. Double doors created airlocks, preventing heat loss. Frame deflection logged under 3 inches at peak wind loads. The measurement demonstrated structural integrity. 3 inches represented controlled flex, not damage. The structure absorbed stress through elastic deformation, then returned to original shape. That behavior indicated design within safe stress limits. Snow load tests measured performance under 40 pounds per square foot or greater. Heavy snowfall in the Aleutians could accumulate rapidly. Flat roofs failed under snow load regularly. The curved Quonset profile naturally shed snow. Accumulation was minimal, even during heavy snowfall. The aerodynamic shape that resisted wind also resisted snow loading. Aleutian base commanders reported operational use through winter with acceptable fuel consumption. The insulated variants weren't perfect. They required heating in extreme cold. But they were habitable, which mattered more than efficiency in environments where alternatives were worse. Test memoranda confirmed capability across climate extremes. The same basic kit family, with appropriate modifications, supported operations from Arctic to equatorial conditions. The versatility simplified procurement and training. Supply officers managed one shelter system with variant configurations instead of completely different structures for different climates. Logistics tables showed common spare parts across climate kits. Panels, ribs, fasteners remained identical. Insulation, ventilation, and heating varied by climate, but attached to the same basic structure. The commonality halved stockage requirements for remote bases. That reduction simplified logistics significantly. The confirmation that one geometry worked across environmental extremes validated the fundamental design decision. The semicircular arch wasn't optimal for any specific condition. It was adequate for all conditions. That adequacy delivered value through versatility. 1944 through 1945. Dahlgren Proving Ground, Virginia, and Central Pacific airfields. High-speed film captured shock propagation across corrugations during blast testing. The footage ran at thousands of frames per second, revealing material behavior invisible to normal observation. The steel panels flexed in waves as pressure fronts passed. Deformation was temporary. The panels returned to shape after the shock dissipated. The expectation was fragility. Lightweight structures shouldn't survive explosive force. The results contradicted that assumption. Quonsets absorbed and deflected blast energy without catastrophic failure. Near-miss artillery and demolition charges produced overpressures approaching 5 pounds per square inch at structure locations. That pressure level destroyed wooden buildings and collapsed tents. The Quonset's curved surface and flexible panels converted what would be destructive force into controlled deformation. Sandbag skirts and partial berming further reduced blast effects. The modifications created standoff distance between explosive force and structural elements. Earth and sandbags absorbed energy that would otherwise hit the building directly. Ordnance engineers documented damage control procedures. Standardized panel swap procedures enabled field repairs. Rib replacement techniques allowed structural repairs using standard components. The procedures assumed untrained personnel working with hand tools under field conditions. Damage control worksheets tracked man-hour restoration timelines. A Quonset with panel damage could return to service within hours of battle damage. That turnaround was shorter than the time required to rig replacement tents. The comparison demonstrated practical advantage beyond theoretical capability. Airfield maintenance chiefs reported operations continuity. Hospitals remained functional under bombardment. Control towers stayed operational. Supply depots preserved contents despite nearby explosions. The preserved capability maintained sortie generation rates during contested operations. Maintenance ledgers documented specific incidents. A Quonset near a bomb impact suffered panel damage. Repairs took 4 hours. The facility resumed operations the same day. The timeline contrasted sharply with alternatives. Wooden buildings, destroyed by similar impacts, required days for reconstruction. The high repair speed preserved operational capability during intense combat. Forward airstrips under regular attack could maintain operations if facilities survived and could be repaired quickly. The Quonset met both requirements. The testing confirmed that blast resistance wasn't absolute. Close hits destroyed Quonsets like any structure, but near-miss survival was excellent. That performance level meant facilities remained operational under conditions that would have destroyed alternatives. April through June 1945. Okinawa, Ryukyu Islands. A CB materials dump showed stacked crate pyramids awaiting distribution to Yontan and Kadena airfields. The inventory represented thousands of Quonsets ready for deployment. Amphibious operations planners factored assembly timelines into infrastructure schedules. The planning assumed enclosed capacity would be available within specific timeframes. The expectation was weeks to achieve operational facilities. Traditional construction projected 30 to 45 days before covered storage and working facilities would be available. The Quonset program delivered faster. Approximately 3,000 huts were erected within 45 days of landing. That pace provided hospitals, radar installations, and repair shops supporting immediate operations. The infrastructure appeared almost as fast as the forces that needed it. Naval Construction Regiment commanders coordinated assembly priorities: medical facilities first, communications second, supply and maintenance third, housing last. The prioritization reflected operational necessities. Personnel could sleep in tents if necessary. Surgical capabilities and radar coverage couldn't wait. Storm tie protocols, standardized anchoring procedures. The Okinawa campaign occurred during typhoon season. Facilities erected quickly, needed to survive severe weather. The storm resistance proved critical when multiple typhoons struck during the campaign. Dispersion patterns reduced risk from shelling. Facilities spread across the airfield area rather than concentrated provided resilience. Artillery hits destroyed individual structures, but couldn't eliminate entire functional areas. The distribution reflected lessons learned from earlier campaigns. Integration with SCR-270 and SCR-527 radar sites demonstrated infrastructure flexibility. Radar required controlled environments. Electronic equipment degraded rapidly if exposed to weather. Quonsets provided the environmental protection, enabling radar operations in forward areas. Aviation maintenance lines incorporated Quonset facilities as standard components. Engine overhaul, structural repair, electrical work, all required covered working spaces. The maintenance infrastructure directly supported sortie generation capabilities. Corps engineer summaries linked sheltered depots to sustained operations. Supply continuity depended on weatherproof storage. Okinawa's tropical weather and intense combat made that protection essential. The infrastructure enabled operations that logistics exposure would have prevented. The campaign experience provided final validation. Quonset facilities supported the largest amphibious operation of the Pacific War. The infrastructure performed under maximum stress. Medical facilities treated casualties continuously. Supply depots supported consumption rates that would have overwhelmed exposed storage. Communication and radar facilities operated throughout despite weather and combat. End-of-campaign reports attributed operational tempo to infrastructure quality. The assessment noted that covered, dry, and repairable facilities mattered as much as fuel and munitions tonnage. That evaluation represented fundamental recognition. Logistics infrastructure wasn't support for operations. It was an operational capability itself. 1946 through 1952. United States, multiple sites. War Assets Administration brochures listed surplus Quonset huts for sale to municipalities, universities, and private buyers. The marketing was straightforward. Proven military equipment available for civilian use. Prices reflected surplus liquidation rather than commercial value. The structures built for combat fronts were redeployed to solve domestic challenges. The transition from military to civilian use happened rapidly. Veterans returning under GI Bill provisions needed housing immediately. Universities enrolling those veterans needed classrooms and dormitories. Communities needed temporary facilities, while permanent construction caught up with demand. University housing directors at Stanford, Harvard, and Michigan State purchased hundreds of surplus Quonsets. The structures appeared on campuses within weeks, configured as student housing, classrooms, and administrative offices. The temporary expedient was expected to last months. Many remained in service for years. Conversion kits adapted military interiors for civilian use. Interior partitioning created rooms within the open arch space. Heating and electrical retrofits provided comfort systems. Plumbing installations enabled bathroom facilities. The modifications were straightforward because the basic structure accepted alterations easily. Zoning variances allowed temporary structures in residential areas normally restricted to permanent construction. The housing shortage was acute. Traditional building couldn't meet demand quickly enough. Quonsets filled the gap, providing immediate shelter while permanent housing was planned and built. Army Corps of Engineers estimated over 170,000 surplus units were repurposed for civilian use. That number exceeded the population of many cities. The surplus equipment solved the national housing crisis through simple repurposing of military infrastructure. Campus maps from the late 1940s showed Quonset villages housing hundreds of families. The concentrations created temporary communities. Veterans and their families lived in surplus military structures while studying under GI Bill benefits. The arrangement worked because the structures provided adequate housing quickly. The wartime modularity transitioned seamlessly to civilian reconstruction. Structures designed for rapid military deployment adapted easily to rapid civilian deployment. The logistics advantages that made Quonsets valuable militarily, standard components, simple assembly, flexible use, made them equally valuable in civilian applications. Enrollment spikes were absorbed not by brick construction, but by corrugated steel. University expansion that would have required years of building happened in months through surplus Quonset deployment. The speed enabled educational institutions to serve returning veterans without delay. 1950s through present. Worldwide. A still-standing Quonset at a former air depot sits beside a modern disaster relief arch shelter. The visual comparison is striking. 70 years separate the designs, but the fundamental concept, semicircular corrugated arch, remains identical. The continuity demonstrates design validity. The structures designated temporary often provided decades of service. Quonsets erected in 1943 remained operational into the 1970s and beyond. Some survive today, testament to durability that exceeded design expectations. Climate conditions from Alaska to Africa proved the environmental range. Cold War site engineers employed Quonset principles for radar stations and communications facilities. The Arctic DEW line used semicircular structures descended directly from wartime designs. Antarctic research programs relied on similar architecture. The aerospace industry studied prefab and arch principles for habitat concepts. The underlying engineering remained sound across applications. Low-mass structures reduced transportation requirements. Aerodynamic load paths minimized structural weight. Kit logistics simplified deployment. Repairability reduced lifecycle costs. Those principles applied equally to military bases, research stations, and civilian applications. Rear Admiral Ben Morale stated in 1946 that the Quonset Hut demonstrated engineering simplicity could be a weapon of war. The assessment captured essential truth. The structure's value came not from complexity, but from optimization. Every element served its function without excess. The wartime engineering response shaped post-war architecture. Prefabricated modular structures became standard in construction. The concept of buildings as assembled systems rather than constructed monuments traced directly to wartime experience. The Quonset represented early proof that manufacturing methods could apply to architecture. Modern humanitarian logistics incorporate arch shelter designs descended from the Quonset. relief organizations deploy rapidly erected structures following natural disasters. The designs reflect lessons learned 7 decades earlier. Curved profiles resist wind. Standardized components simplify assembly. Lightweight materials reduce shipping costs. The production statistics remain staggering. Over 150,000 units, manufactured during wartime, represented more than 144 million square feet of covered space. The throughput demonstrated industrial capacity applied to building production. The scale exceeded anything attempted previously. The legacy persists in unexpected applications: modern disaster response, portable housing, agricultural storage, recreational facilities. The semicircular arch appears wherever rapid deployment and weather resistance matter. The design's validity across applications validates the original engineering decisions. The final measure is longevity. Designs proven by time demonstrate fundamental correctness. The Quonset Hut has been continuously employed for over 80 years across global environments. That longevity proves the engineering succeeded completely. A self-supporting corrugated arch, validated by laboratory tests and confirmed by field experience, enabled rapid weather-resistant bases across the Pacific. The structure sustained medical care and sortie rates under bombardment. It sheltered families and students after the war. Its influence continues in modern prefabricated and disaster response design. The underlying numbers remain compelling. Assembly time measured in hours. Shipping weight under 4 tons. Wind resistance to 130 miles per hour. Repair time under 4 hours. Those specifications solved human problems in 1942. They solve similar problems today. If you value fact-checked military engineering history grounded in archival evidence, consider supporting the channel. These stories preserve the memory of those who served, documenting how industrial capacity and engineering excellence combined to achieve victory. Share your perspective in the comments, because every memory and reflection keeps this history alive.